when Jake did this, you get the replacement half wide open, but like,
I got like
brilliant.
half an hour.
Someone who should have been on the slides apparently.
James is like working with James as part of his master's project.
Got it. Okay, right, we're going to start then. Back fast. Right, hello everyone. Welcome back to SLS. This time around, we have Dr. Nathan Evans, and he's just going to talk a little bit about his work on JWST. But I'll let him talk a bit more about that. So everyone, let's give a round of applause.
Cool, yeah. There is a clicker, but there doesn't seem to be the USB thing for the clicker, so I might have to jump backwards and forwards between the laptop or stand all the way over here. So I'm going to talk to you this afternoon about some of the first results from JWST, which is all very exciting, and it's scary to think that JWST is like 3 years old at this point. I moved to Manchester 6 months before JWST launched, and so it was kind of just a bit rabbit in the headlights of, like, I finished my PhD in a slightly related but not JWST related topic, and then it's like, oh, by the way, you're now working on a $10 billion telescope, it launches in 6 months, get prepared, because everybody also wants to work on this. So yeah, all very exciting, but I'm going to talk to you sort of an introduction to why it is that we want to study the early universe in particular, because this is the subject area that I study, mostly from an observational point of view. I'm not really a theorist. I like dealing with data and raw imaging that comes out of telescopes and things like that. But give a brief overview as to why do we want to study the universe, what science is there that we still don't understand, or what outstanding questions are there that we want to answer. I'm going to go into how we use telescopes such as Hubble and JWST to study the universe. In particular, how do we identify galaxies that are really, really, really far away. Then give you a brief overview of what JWST actually is, the James Webb Space Telescope, in terms of its design and why it's very suited for doing this kind of research and why everyone's very excited about it. Then talk a bit about what we first found within the first maybe 3-4 months with JWST. Talk a little bit about what went well. Lots of people like to talk about what went well, but I also like to talk about what didn't go so well with JWST, because it wasn't the most perfect start. There were issues with calibrations and various things like that. And I like to make sure that people are aware of this sort of thing. And I'm going to finish up with a bit more of what the state of the field is now, and in particular what contributions the group in Manchester has played towards the findings that we've had with JWST. So this is a broad timeline of the universe, I guess, starting from the Big Bang all the way on the left-hand side through to the present day on the right-hand side after about 13.8, 13.7 billion years or so. And the bit that we're going to be interested in is the sort of the first billion years of the universe, so from here to the left-hand side. We want to understand how galaxies and stars first formed, and we want to understand more about the Big Bang and things like that. But there are a few problems with this. For starters, the Big Bang itself in the first 300,000 years or so, the universe is what we call fully ionized. So the initial universe after the Big Bang is extremely hot, tens of thousands of degrees or even hundreds of thousands of degrees. And as a result of this, electrons and protons, things like that we see today form atoms, be it hydrogen, oxygen, carbon, etc. Are too hot to actually form atoms. You just have a soup of electrons and protons flying around. The problem with having this primordial soup that people call it is that light can't travel through a soup of free electrons and protons. Protons and electrons absorb light. So we have a universe that's opaque. So we can't see anything using a telescope, no matter how powerful the telescope. Within the first 300,000 years or so of the universe, because the universe is too hot and all light gets absorbed. When the universe hits, so everything that we understand about the first 300,000 years of the universe or so comes purely from theory or extrapolating what we find elsewhere in the universe. When the universe hits around about 300, 400,000 years old, the average temperature of the universe is expanding, and as it expands, as the thermodynamics cools down. As it cools down, we end up hitting a temperature where atoms can start to form. The protons, neutrons, and electrons start sticking together, forming hydrogen and helium for the most part, in what we call nucleosynthesis, so the formation of the first nuclei or atoms. And at this point, light is allowed to now travel because there aren't free protons or electrons flying around anymore, absorbing all the light. And this releases something that we call the cosmic microwave background, which some of you may have seen this image before, a very famous image. And what this essentially is, it's a black body spectrum, so the spectrum that a warm thing gives off. As it, like you have a hot piece of iron that starts glowing red, and the hotter it gets, the sort of bluer it gets. Like you see blue flames are hotter than red flames. This is a black body spectrum of something that's 3,000 degrees, or something like that. It's not 3,000, it's more than that. And over time, it has cooled down to a temperature of around about 2.7 Kelvin, or 2.7 degrees above absolute zero. So this is mostly in the microwave and radio that this emission kind of propagates through the universe. And what we see now is that if this is the leftover, this is the first thing we can see after the Big Bang. The main thing that this tells us is that the universe is lumpy. It's not completely flat and uniform. We're seeing pockets where the universe is warmer and pockets where the universe is colder, which is what the colour diagram is here. And this forms the seeds of what will eventually collapse down to form like large-scale structure in the universe, and eventually within that large-scale structure, galaxies and things like that. So after what we call recombination, when the cosmic microwave background is emitted, we have something called the dark ages. We just have hot gas that's swirling around, slowly condensing to form large-scale structures, and then eventually galaxies and galaxy clusters. But until the very first stars formed, the universe is just made up of this hot gas, and that's about it. So we call it the dark ages because there's nothing kind of there actively emitting light aside from just gas floating around. And it's only until after a couple hundreds of millions of years, so we go from a couple hundred thousands of years to a couple hundred millions of years, maybe 100, 200 million years or so, that we think the very first stars start to ignite or like collapse down and start nuclear fusion. And so we see the first stars and the first galaxies start to pop out, we think, at around 200 million years. That's what the theory says anyway. And so we end up with this region, which is the region that I'm most interested in, that is the formation of the first astronomical objects, the first stars, the first galaxies. And a lot of people dub this region of time reionization, so it's from around about 200 million years to 1 billion years. And this is because we've gone from a universe that's ionized to start off with. It's very hot, hundreds of thousands of degrees, cools down, and then becomes, quotation marks, neutral. We have hydrogen and helium. But then when we start having stars introduced, stars like to emit ultraviolet radiation, as we've come to learn through the sunburn. And ultraviolet radiation reionizes hydrogen and helium that's kind of around all of these galaxies. And so around baby galaxies, we have bubbles of ionized gas being formed as the young stars throw UV radiation out into the universe. And after about 1 billion years or so, that process finishes. We end up with a universe that's again made of naked protons and electrons outside of galaxies. And we end up with the modern day universe. I hope that really makes sense. After that. And so we're trying to understand this sort of section in the middle here, although this is on logarithmic timescales. This is the first sort of 1% to 10% of the age of the universe is kind of the region we're trying to understand. How did the first galaxies form? How long did this process called reionization take? What were the first stars like? We expect the universe to just be made of hydrogen and helium, so we expect to be dealing with stars that are only made of hydrogen and helium. Do they behave differently or have different lives to the stars that we see today, like our sun, which contain carbon and oxygen and things like that? Yeah, so these are the sort of questions that we're trying to answer. When exactly did the first stars form? Are these stars made up of only hydrogen and helium? Theory predicts that they should only be that, but if we're finding metals really in the universe, we have to then explain how do those metals get formed. I would say metals in the loose astronomer term, where anything that is heavier than helium is a metal in our case, so carbon and oxygen is classed as a metal. And then, do the very first stars behave differently to the stars that we see today? Do they have shorter lives, longer lives? Are they bluer? Are they redder, etc.? How fast did galaxies grow and form in the first place? How fast were metals produced? And how fast did galaxy structure form? So things like spiral arms and things that we see today in the modern day universe. How long did it take for these structures to form? So why couldn't we do this with Hubble? The next sort of handful of slides are going to kind of explain this. But Hubble can only see galaxies up to when the universe was around about 400, 500 million years old, so kind of in the middle of this time period that we're interested in. And James Webb has been, well, one of the main intentional reasons it's designed is to push this further back. So with Hubble, we could see galaxies so distant that we could see them when the universe was only 500 million years old. With James Webb, we can push that further back to when the universe was only about 100 or 200 million years old, around the time that we think galaxies should be forming for the first time. So this is one of the main design goals for JWST. But why, there are sort of four concepts to understand as to why, why Hubble has this limitation and why we need JWST to push this, what we call the redshift frontier, or see galaxies that are further away. So the concepts that we need to understand are the speed of light, the Doppler effect, this concept of redshift, and the idea of there being an expanding universe that we live in. And these four things combined help us to study the early universe and also put limitations on how much we can study the early universe. So the speed of light is something that we've known about for over 100 years now, is around about 300,000 kilometers per second. And the idea is that because there is a fixed speed of light, the further away something is from you, the longer it's taken for that light to travel to get to you. So the GPS satellites are a couple tens of thousands of kilometers away, and it takes about 0.12 seconds for your telephone to signal to a GPS satellite and for that to then bounce back down again. This is a relatively short time scale, and we don't notice it in real time. But when we start to go into distances of the scales that we work with in astronomy, then the speed of light becomes quite impactful. So distance to the sun is 150 million kilometers, and this means that it takes about 8 minutes for light from the sun to reach the Earth. And so if the sun were to just completely vanish for some inexplicable reason, we wouldn't actually know for 8 minutes or so, because the light that we're seeing right now in the middle of the day, if it wasn't so cloudy outside, is the light that the sun emitted 8 minutes ago. And this concept keeps going. So the Alpha Centauri, which is the nearest star to us that isn't the sun, it takes about 4 years for the light to travel to us. And then when we start getting to the distance scales, we're talking about other galaxies, it's millions of years and then billions of years the further away the object is. And so what we want to do, if we want to look at galaxies that existed, or study galaxies that existed when the universe was really young, if we want to find galaxies that are the furthest away from us. Because the light from those galaxies has taken 10 billion, 11 billion, 12 billion, 13 billion years to reach us. And so we're seeing the light from that galaxy as it was that long ago. So if we can find the most distant galaxies, we can observe what those galaxies looked like when the universe was only 5% of its current age, or even younger. Another concept that we need to understand is the Doppler effect. So most of us know the Doppler effect every day through its application to sound. So be it a race car or an ambulance or anything like that, as something drives by very fast, you hear this rise in pitch and then decrease in pitch as something approaches you and then travels away from you. So an ambulance driving towards you starts going woo, it gets louder and higher pitched, and as it's moving away from you, it gets lower pitched. Because light and sound both behave as waves, the same concept applies to light. Except because the speed of light is so much faster than the speed of sound, the speeds that's needed to have this impact are much higher. And so we don't see this in everyday life, where something moving towards you very fast doesn't look bluer and something moving away from you very fast doesn't look redder. But the running joke in astronomy is that if you see a blue stop sign, then you probably are definitely going way too fast. But yeah, so the idea is that something moving away from you is going to look red, and something moving towards you is going to look blue. And yeah, we don't see this in everyday situations, but in the scale of astronomy, where we have things moving around at hundreds of thousands of kilometers per second, this can be a noticeable effect. And then, sort of final thing or second final thing, is the idea that we live in an expanding universe. So this is something that won the Nobel Prize in the 80s or 90s, I'm trying to remember when it was now. But we live in a universe that's expanding, and the way that we realize this is through something called type 1a supernova. So this is an example of a type 1a supernova on the left-hand side. It's a very particular kind of supernova that occurs when you have two stars that live close together. One star is a white dwarf, and one star is a red giant. And as a red giant ends its life, it expands. As it expands further, material can be transferred to its little neighbour, as it kind of being shown here. And when white dwarfs hit a very particular mass, then they explode in a type 1a supernova. And these supernovae always explode with the same brightness, because these white dwarfs always explode at exactly the same mass, exactly the same amount of energy is released, and exactly the same luminosity. And so we can use these as what we call standard candles. So it's like taking a candle nearby, is quite bright, and as you move further away, it gets fainter and fainter. And how it gets fainter is by the distance squared. And so we can use these to plot distance. So the further away a type 1a supernova is, the fainter it is, and so we get a distance measure out of that. And we can also get a velocity measurement out of redshift, or the idea of the Doppler effect. So something we could see, we have a blue type 1a supernova, something's moving towards you, or a red looking type 1a supernova that's moving away from you. And if you plot the combination of the two, so the velocity the object's moving at, and distance, we see that the further away something is, the faster it's moving away from you. And so the only main explanation for this is that we live in a universe that's expanding. The further away something is from you, the faster it's moving away from you. The expanding universe theory kind of comes down to that. And that's what this kind of diagram shows here, that it's a nice straight line, whereas the further away something is, the faster it moves away. And so we can combine all of this together, where we want to study the most distant objects in the universe. And so if we want to identify what objects are the most distant, we want to find what objects are moving away from us the fastest, because we want to go as far along this x-axis as possible, the greatest distance. And so this will also go the furthest up here, this straight line continues. We want to find things that move very fast away from us. And so this is what the concept that we use to find galaxies that are in the early universe. We use this concept which is called redshift. So the further away something is from you, the faster it's moving away from you, and thus the redder it appears. And so we use a quirk of quantum mechanics, which is that elements such as hydrogen, helium, oxygen, carbon, etc., like to absorb light or emit light at particular frequencies, causing their electrons to bounce up and down within the orbits. You can't imagine the classic orbit model of an atom where you have electrons orbiting a little nucleus. Particular kinds of energies of light allow these electrons to bump up and down in those orbits. And what this does is it allows us to have unique patterns describing each element appear in sort of a rainbow of light. So if you were to shine just purely white light or a rainbow of light at carbon, I'm just making this up here, you would see a pattern of absorption at particular frequencies where electrons within carbon are absorbing light and jumping up into higher or more distant orbits. And so this could be an example for carbon, and then oxygen would have a different pattern of lines, nitrogen would have a different pattern of lines. And what we can do is we can use these patterns to A, figure out what something's made out of, be it a star or a galaxy or anything like that, and B, measure how fast it's moving away from us, because these lines will be shifted redder the faster it's moving away from us. And so the more distant the galaxy is, the faster it's moving away from us, the more these lines are shifted to the red. Then again, more distant, the lines will be shifted even redder, more distant again, the lines are shifted even redder. So what we're trying to find is we're trying to find galaxies where, say, they're made of hydrogen, helium, carbon, etc., that have been shifted as far red as possible. Because that means they're traveling the fastest away from us, which means that they're probably the most distant as a consequence of the expanding universe. But there is a bit of a problem with this method, and sort of taking a galaxy and putting its light through a prism, like we see on the bottom left here with the Pink Floyd album, is expensive. When we say expensive, we mean this in terms of time taken to do this with a telescope. The further away a galaxy is, the fainter it's also going to be. And so in order to get enough light to make this sort of diagram that we see here, it can take hours of time on a telescope for these patterns of absorption or emission lines to show up. And for the last 30 years or so, we've only really been able to do this process on one galaxy at a time. So when it's taking 8 hours per galaxy, you can only do it one galaxy at a time. That is very slow, and you're dealing with a needle in a haystack problem, where the galaxies you're interested in are very rare, and you're spending lots of time pointing your telescope at objects which are what we call low redshift or sort of local universe galaxies. Nowadays, we're getting new instruments that can do this better. We have what we call multi-object spectrographs, which can do a few hundred galaxies at a time, and the most modern ones, which will be starting in the next few years, can do maybe 1,000 or 2,000 galaxies at a time. But there's still a bit of a needle in a haystack problem with this, and it's a lot of time to try and identify these galaxies. So is there a method that we can use to find high redshift galaxies, or the most distant galaxies, that skips needing to use spectroscopy, which is the method that produces this diagram here? And thankfully, the most abundant element in the universe, hydrogen, is here to save the day. So the Lyman break is something that we use to identify high redshift galaxies without the need for putting a galaxy's light through a prism and observing a rainbow and looking for patterns. The Lyman break is caused by hydrogen, which is the most simple element and the most abundant element of just a single proton or a single electron absorbing light. And it so happens that hydrogen, the single electron that's in hydrogen, will absorb any and all light that is bluer or higher energy than about 121 nanometers, which is in EUV. And so all light bluer than this, hydrogen will like to absorb, and what this process does is kick the electron out. So we have a proton, an electron, any light bluer than 121 nanometers will be absorbed by the electron, it will then get kicked out, and you have just any proton electron flying around. And the further away something is from us, the more sort of quotation marks empty space there is between us and it. So hydrogen, lots of people like to say that the universe is empty in quotation marks, but the universe isn't really empty. There are trace amounts of hydrogen floating around in space between galaxies. And so the more empty space there is between us and a more distant galaxy, the more hydrogen there is, the more of this blue light is being absorbed over time. And so much light can be absorbed that instead of having to look at spectroscopy or sticking light through a prism and seeing the rainbow, we can see this impact in imaging. So if we take images in like a blue filter, a green filter, and a red filter, galaxies that are really far away, we're going to have this absorption feature, which is very, very deep, shifted redwards, to the point where the galaxy appears to just completely disappear in the blue filters, which hopefully is an example of what's next. Yes? Hopefully this video will play. I will pause it when it gets going properly. Okay, 1 second. Jeez, time's going fast. Come on. Right. So, what we've got here are filters from the Hubble Space Telescope. So the Hubble Space Telescope is mostly an optical telescope. It can see things from between 0.4 microns and about 1.5 microns. The optical regime is about 0.4 through to about 0.8 or so, 0.7. So this is blue, this is sort of green here, and this is red here, and this is starting to go into the near infrared over here. And this is an example of a galaxy spectrum. We see some of these absorption features caused by example elements, not sure which ones are here. But then this feature here is what we call the Lyman break, or I think it might actually be this one. It's the Lyman break. So this is caused by hydrogen absorbing everything bluer than it, and you'll see that as the galaxy moves further away, it gets redshifted more, because its universe is expanding. So this feature will shift to the right, the further the galaxy gets away from us. And as the galaxy is further away from us, there's more hydrogen between us and it, and so all the blue light gets increasingly absorbed as well. Blue ones of this feature. Is this going to play? Yes. Okay, this is explaining as well. At the bottom here is like what we see with a galaxy taking images through these filters. And so you see the further away the galaxy is, the more it drops out in the bluer filters. So we can take large images of the sky using Hubble, James Webb, or any telescope through a series of filters and look for galaxies that seem to disappear in the bluest filters. And the more blue filters, or increasingly redder, that it disappears in, the chances are the higher the redshift, or the further away that galaxy is. And so we can use that to pin down which objects are most likely to be very high redshift and follow them up with the spectroscopy method before, rather than spending excessive amounts of time trying to get spectroscopy of every single object in the sky. And this is the sort of main method that I work with. I do sort of large-scale population statistics with these galaxies, and it will take way too long to get spectroscopy of hundreds of thousands of these objects, so I rely on this method to identify galaxies of very high redshift. Ooh. Yes, so this is where JWST comes in very useful. So Hubble, as I said, is mostly a UV or optical telescope, and this means that it can only see this Lyman break up to around about 1.5 microns or so, which is when the universe was around about 500 million years old, or what it would correspond to in terms of how far away the galaxies are. Whereas what JWST does is it expands this way into the near infrared. So this is the filter set from JWST on roughly the same sort of scale. And so we can see galaxies that have dropped out in even in redder filters compared to before. And so a galaxy that existed when the universe was only 2% of its current age would appear in these three filters here, but disappear in all of these filters. And the Hubble wouldn't be able to see it at all, because it would disappear in every single one of the Hubble filters. And so yeah, this is how we need JWST in order to study galaxies so distant that we see them when the universe was younger than 5% of its current age. So a bit about JWST itself. Hubble hadn't even launched yet, and there was a conference in Baltimore in the United States about building Hubble 2, and what would eventually become JWST. The first name it was given was the Next Generation Space Telescope. But this happened in 1989, and then 10 years later, after Hubble was fixed and under full operations, NASA allowed the Next Generation Space Telescope to go under concept design and various reviews. And then in 2005, the design was finalized. There was a budget given of $1 billion. Ha ha ha, that didn't last very long. And construction began with a launch date of 2014. Ha ha ha, that didn't last either. So it was Christmas 2021 when it finally got launched, smashing its budget by a factor of 10 because of various issues and delays. But the concept and building stage took around about 25 years. There were 4 science instruments, or 4 different kinds of cameras on JWST. Around about 1,200 people were involved in its construction across 14 different countries and many companies within those countries. And the UK was very heavily involved in its construction as well. One of the 4 main cameras was just built in the basement at Edinburgh University. And one of the other cameras was built in the basement of an American football stadium in Arizona, because the funny story is they couldn't convince the university to allow them to build a new engineering facility, but they could convince the university committee to build a new football stadium. So they presented them with a design for a football stadium that had clean rooms and labs in the basement, and they gave it the thumbs up. The wonders of American institutions. And so after launch in Christmas 2021, there were 6 months where the telescope traveled to its orbit. Hubble orbits only around about 300 kilometers up. The reason that it does that is to make it accessible for repair, because Hubble was made during the time of the space shuttle. So Hubble was only put into that orbit so it could be easily accessible. But it's not the most ideal orbit for science, because you have to deal with the moon and the Earth constantly being in the way and dominating large portions of its field of view. We don't really have the space shuttle anymore, so James Webb was designed not to be serviceable, and we instead stuck it in orbit around about 2 million miles away, or about a factor of 10 or so further than the moon, in a stable orbit that's called L2. Rule number 1 of spacecraft design is to minimize the number of moving parts, because moving parts break, and you can't fix things generally in space, especially without the space shuttle. And so James Webb ignored this by having 344 moving parts that could fail, and if any one of them failed, then the Space Telescope wouldn't work, which made everyone very nervous, but thankfully it did work. The sun shield, the mirror is about 6.5 meters wide, but the sun shield, that's what this at the bottom is, so this is always facing towards the sun, is about the size of a tennis court. And all of this was packed up and folded up like origami in order to fit into the top of the rocket because it was too big to fit. It was then cooled down to about minus 230 degrees Celsius over the course of 6 months because the telescope works mostly in the near and mid-infrared, and warm things glow in the infrared. So you need this telescope to be as cool as possible, else the camera's just going to see itself. But yeah, so this was 6 months, and then after 6 months, it was showtime, and then there was this extremely cringe-worthy press conference with Joe Biden, where they showed the first image that JWST produced. And luckily for me, the first image that JWST produced was a deep field. Yes, just what I wanted for science. The launch went incredibly well. The accuracy of the rocket launch was so good that JWST barely had to use any of its own onboard fuel to get itself into the right orbit. And so the time span that we originally gave it of 10 years has actually been extended to about 20 years before the telescope will start having such a low amount of fuel it won't really be able to orientate and turn itself particularly well anymore. But yeah, this is good news. And then this was the image that was produced, the image of the galaxy cluster. It was called SMAX 0723, great name. But what we have in the foreground in these sort of big elliptical sort of yellowy orange galaxies here are galaxies in the foreground, very massive galaxies, and in the background basically everything that's orangey red is probably high redshift behind it. This was all very cool. Everyone clambered over it to do science immediately. Even before the image was released, people were trying to do science on the JPEG and like look for the reddest things, such as this thing here. But yeah, as soon as the actual images were released, we started looking for high redshift galaxies, and we found 4. 4 that were dotted around in this image. And you can kind of see in this scale what I mean by the needle in a haystack problem, where there are 4 galaxies that are located so distant that we're seeing them when like 11.3 billion years ago, 12.6 billion years ago, 13 billion years ago, 30.1 billion years ago. These things are tiny, even with JWST, the size of the telescope and all the engineering that's gone behind it, these things still look like tiny little red blobs. The red makes sense because they're so far away, but we also expect these things to be very small because we're expecting to find baby galaxies in the process of forming. Yeah, so we found 4 objects, high redshift, and this was cool. Everything looked great. And then over the first 3 months or so, JWST went and did a bunch of deep fields. This is another deep field that's called GLASS. And as all of this data was being taken, a lot of it went public immediately. So as soon as the data was taken, it was downloaded back down to Earth. It gets stuck on an archive and is made public immediately. And so lots of competing research groups around the world were all jumping on the same data at the same time and racing each other. It was fun, but also very stressful, trying to write a paper in 8 days, which is what the timescales were. And it was the point where 11 papers a day were being submitted to journals, and journals were being absolutely overwhelmed with the fact that they were getting so many papers submitted to them, but no one was wanting to do peer review because everyone was working on their own work. Eventually things have calmed down after about a year, but yeah, it was a crazy time. And the cool thing was we were finding loads of galaxies at these distances, but we were finding maybe too many galaxies at these distances compared to what we were expecting, and that's something I'm going to touch on a little bit later. Another thing that we found was that a lot of galaxies at sort of great distances that we thought looked weird and clumpy and messy and generally unstructured with Hubble, when we revisited them with JWST, looked very organized and structured. So on the left, this is some work that I led with Leonardo Ferreira, who was a PhD student in Nottingham at the time. And on the left-hand side, you see what some of these galaxies look like with Hubble. In particular, focusing on the top 2, and these left bands, where you see these galaxies just look like clumps, random clumps of stuff, and not really organized or anything like that. And in Hubble's reddish band, you maybe see they look a bit diski-like, and that might be spiral arm or something here, but it's hard to tell. So with JWST, with a higher resolution and being able to go even redder, we see that a lot of these galaxies are very structured, and we see spiral arms and things like that. And we see spiral arms and galaxy disks existing when the universe was only about 10% of its current age, which surprised quite a lot of people, and it wasn't predicted in some of the simulations that we had. Some did predict it, some didn't predict it. And this was already showing that JWST could discount some ideas or physical theories that we had for how galaxies formed, even just by looking at things by eye and saying, hang on, these galaxies have spiral arms. Another thing that we learned is that some of these galaxies can be chemically complex. So this is an example of the rainbow plot that I showed earlier. A bit blander, but the left side is blue and the right side is red. And we're seeing here little peaks of emission coming from various different elements. With Hubble, we could only see up to about here and leftwards. So we could just about, this is the most distant galaxy that Hubble had discovered, and we could see this bit, and that was it with Hubble. Whereas JWST allows us to extend this coverage up to 5 microns in the near infrared. And what we see is that this galaxy that existed when the universe was about 400 million years old or so already has nitrogen, carbon, oxygen, and even magnesium in it, which is very heavy, and neon over here, which surprised lots of people as well. This was one of the first spectra data by JWST, and it showed that when the universe was about 4% of its current age, some of these heavier metals, like magnesium and neon and things like that, were already existed and were present in galaxies. I think that's, yeah, just highlighting magnesium and neon there. There were some problems with some early JWST work. This is a newspaper headline here, a bit of panic, where lots of people jumped on the very first images that JWST made and started trying to find the most distant galaxies and things like that. Now, one thing we didn't realize is we assumed the telescope was calibrated properly by NASA, and that was not the case. So we probably should have checked the telescope was calibrated first before we all started just rushing to the science. And we found out after about a month or so that there were errors on how bright the pixels should have been by about 20% or so. So we thought some galaxies were brighter than they should have been by about 20%, some galaxies were fainter than they should have been by about 20%. And so all of the work that was done in the first 2 or 3 months had to be redone again, and the journals, I'm sure, had a great time with not only being swamped with lots of submissions, but also having been swamped by lots of people retracting their papers and then resubmitting them again with the fixed versions. But there were a lot of issues with calibrations to start off with. Within the first couple of months, we managed to pin it down from 20% error to about 5% error, but it still took about a year before the errors got down to what they had anticipated them to be in the first place. Even with all the errors fixed, we had a problem of finding too many galaxies at great distances. So within astronomy speak, we usually refer to redshift when talking about this, but essentially the lower the redshift or Z, the closer to the modern day universe it is. The modern day universe is redshift 0, and then redshift 10 is when the universe was around about 500 million years old, and then going higher redshift is going to younger and younger universe. And I've cut the y-axis off here. This is essentially how many galaxies that we're finding as a function of distance or age of the universe. All of these lines that are going down here are all different simulations, and the data points that we're seeing on here are what the first observations from JWST showed. And this is on a log scale, so each of these main steps here is a factor of 10 thereabouts. And so we're seeing that there are about a factor of 10 or even 100 more galaxies being found than some of these models predicted. And so some models said that in the first year of JWST data, we should maybe see 1 or 2 galaxies at redshifts of about 12, and we were finding several in the first 3 weeks, which blew some of these models out of the water and showed that galaxies probably formed earlier than many of these models first thought. Just checking the time. Yeah. There was also another problem of too many galaxies that were very high mass. So this is a cool thing that, as astronomers are great at naming things, these things are called little red dots because they look like little red dots. And when we first found them, people thought they were galaxies and started trying to model them and how massive they were. And in order to be very red, they must have had a lot of mass, and they also must have had a lot of metal-rich dust in them. And what this ended up with is us finding a bunch of galaxies that were very high mass, which is what these red dots are here. So these things are bigger than the Milky Way when the universe was less than 10% of its current age. And it's like, how do you make a galaxy that fast? That's that big. And some say that this was breaking cosmology, like our idea of how the universe works in the first place. You can't make a galaxy that big in that short amount of time. Nowadays, a lot of people think that these are likely to be what we call AGN, or a lot of the light is coming from the accretion disk around black holes. So think of the classic interstellar picture where you have this hot disk of material around a black hole. These can be as bright as galaxies, and we think that the light dominating these red objects is coming from those, like baby black holes that are growing, as opposed to lots and lots and lots of stars. The universe was also, well, we have this idea of using the line and break to find things, and yeah, that's all well and good, but it doesn't always work. So we had this object here, where we measure how bright the object is in different colored filters with JWST. You see there's nothing there, there's nothing there, there's something there that only just, and then there's a bright object here in a few filters. If you fit this with the line and break, which is what this black line is, you get a redshift of 16.2. This was found in the first month, again, with JWST, and everyone went nuts, because we were expecting to find maybe redshift 12 things as the highest thing that we find. This was redshift 16. Everyone was crazy about it. It became one of the first things to have follow-up spectroscopy. And when we did follow-up spectroscopy, it looked like this, the red line instead, not the black line. And it turns out there's actually a galaxy at redshift 5 there also, but it's extremely red and dusty instead. And it just so happened to be very oxygen-rich, which is what these big booming lines are here, that you can just about see. And the combination of it being red and dusty with lots of oxygen made it look like it was a line and break. And so this then raised a lot of alarm bells and people thinking, oh, maybe the line and break isn't as trustworthy as we think it is, and we're selecting things that the redshifts above 10, and then they really redshift 3 to 5 instead. So the early conclusions from JWST are that galaxy formation seems to be at the upper end of how efficient we thought it would be. We've already ruled out a lot of models that said galaxy formation was slow and happened late. We've also ruled out a lot of models that said that galaxy structure was quite slow to form as well, because we're already seeing spiral arms and disky structures in the early universe. We are now being able to see galaxies back when the universe was only about 3% of its current age, but we're also seeing metals and things like that. So did the first generation of stars have very short lives? How did we make these metals so fast? And then little red dots have got lots of astronomers confused as well as to what they are and whether or not they're supermassive black holes in the early universe. Just thinking, another 5 minutes or something, is that all right? Yeah. So I'll spend the next 5 minutes talking a little bit about the work that we're doing specifically in Manchester. And in particular, like this is one of the images that we've made here. So we run a project in Manchester which is called Epochs. It was an acronym that stood for something, but it's already been lost to time, despite the project's only been 3 years old. We can't remember what the original acronym was anymore. I don't think anyone actually wrote it down. But the idea, so this has been led by myself and Professor Chris Consolis. If any of you do the exoplanets module in physics, you'll know Chris. And the idea is that we're trying to uniformly process and analyze every deep field image that JWST takes. With the idea of trying to do large statistical studies with thousands of galaxies when the universe was less than 10% of its age. And so what we want to do is we want to study how rapidly structure formed, we want to study how rapidly galaxies started clustering together to make galaxy clusters and large-scale structures, determine how rapidly galaxies grew, how rapidly this thing called realization happened, and much more. We've analysed about 6 different JWST surveys so far, covering about 10 different patches of sky. And within that, we found around about 1,100 galaxies that existed in the first billion years of the universe. And so with this sample of 1,100 galaxies, this is an example of some of the images that we've made. This is one of the deepest fields that JWST has taken so far. It's called NG Deep. It's about a factor of 2 deeper than the Hubble Ultra Deep Field, thereabouts. Yeah, very cool. This is another one. Some of you may have heard of JADES. If you have looked at JWST before, this is the JADES field, which is about 4 times bigger than the field I just showed previously. It's got lots of objects in it. This is the galaxy cluster that's part of a survey that we've been involved with called PALS. The galaxy cluster itself is called El Gordo, which is Spanish for the big one, or the fat one. Again, we see instances of simple gravitational lensing, where galaxies in the background are being stretched by the mass of the galaxies in the foreground. And then this is another galaxy cluster here. But we have like over 10 of these images now that we're studying. And we're interested in all of the tiny little orange things that are in the background, as opposed to the very pretty things in the foreground. So this is just a highlight of some of the results that we've had. Tom Harvey, a PhD student in our group, kind of came to the conclusion that trying to measure how massive these galaxies are is very hard. So at the top right here, we have a plot that shows the probability of a galaxy's redshift given trying to model this data. So we see a galaxies here, here. A galaxy vanishes in these bands here. And so modeling where the iron break sits between these 2 images, we get an estimate of what the redshift of this object is. So its redshift is about 12, thereabouts. So when the universe was about 400 million years old or something like that. And then we try to model the mass of this object, and the mass is all over the place. This is on a log scale, so every step of 1 is a factor of 10. And as we use some models, all of these models look about the same that we're fitting to these black data points here. By eye, they all look about the same, and the quality of the fit is all about the same. Yes, the mass that you get for a galaxy varies by a factor of 100. And so a lot of people, when they were publishing their first JWST papers, were just running one model, saying that's the mass, there we go, and publishing a paper. And one of the conclusions that we came to was that this is very model dependent on what sort of models you're using, and that your masses could vary by a factor of 100 compared to what people were publishing. And so this very high mass little red dot problem that we mentioned before could partially be down to the assumptions that people are making and how they model the masses of galaxies. Duncan Austin, another PhD student in our group, kind of statistically proved that galaxies get bluer as we go towards higher redshift or a younger universe. This makes sense because blue stars typically live younger lifespans, and we expect the first generation of stars made of mostly hydrogen and helium to typically be high mass as well, something that's within the community we call the top-heavy initial mass function, which is just jargon, but it basically means we expect there to be lots of big blue stars in the early universe. And this trend of galaxies getting bluer, which is what this y-axis is here, blue is at the bottom, red is at the top, and so this is just the colour of the galaxies in the UV light. Galaxies at high redshift being blue wasn't the most expected. We expect it to top out at this colour of about -2.8. So something that we're looking forward to is looking higher and higher redshift galaxies to see if this flattens off and stays at -2.8. Because that is something that we expect the first generation of stars to look like, at least from a theoretical perspective. This was one of the studies on morphology that we did with a master's student, Catherine, who's just started a PhD in Liverpool. So this was showing that galaxies look very disky, even at early times. So this value of n equals 1 here is just a number that describes how the light from galaxies is spread out. And 1 is about what we expect from something called an exponential disk, or something that looks a bit Milky Way-like. And we see that star-forming galaxies in particular, even across all of cosmic time as far as we can tell, look disky, which is very interesting and something that many simulations didn't predict. So that was a cool result from her, even from a master's project. We found that early galaxies also tend to have relatively mature populations of stars. So this is again the same thing of like how bright the galaxy is in different filters. So we see the Lyman break here. A galaxy is not detected in the 2 bluest filters, and it appears here. And then we see in the reddest filter that we've got here another jump up. This is something that's called the Balmer break. This is the Lyman break, and it's caused by relatively old stars that are about 100 million years old or a little bit older. So still relatively young in the time scale of the universe, but for stars, they're a moderate age. And it shows that galaxies that we are finding when the universe was 500, 400 million years old already had stars that were 100 million years old, which gives us an indication these things must have formed at least around about when the universe was 200 million years old or something like that. Given those more constraints of when galaxies first formed. And finally, we were looking for proton clusters or baby galaxy clusters. And we found this one within the Jades field, which I think a couple teams have now also claimed to find, where this is a slightly lower redshift, a redshift 5.5 or so, but still the universe is 8% of its current age, thereabouts at that point. We're finding groups of galaxies at very similar redshifts, forming sort of large scale structures. And in this case, there are 66 galaxies, all with very close redshifts, form these sort of two filaments that are seen here, which we think could be the start of large scale structure. That's pretty much it, yeah. So the conclusions of the work that we're doing is that we need to combine lots of different surveys together in order to understand early galaxies more from a population point of view. All's well and good studying individual objects, but when you study individual objects, you can be biased towards the sort of life that that particular object's had. You could be studying a galaxy that's had a very unique life, or you could be studying a galaxy that's had a very average life, and you don't really know. But by studying thousands upon thousands of them, then you kind of get the average idea of the population. The same as if you study people, or you study any sort of population things. We also confirmed that we're finding more galaxies at redshifts above 10 than many people expected. And this may show that star formation in the early universe was maybe a bit more efficient than many modern stars thought. In only 3 years, the JWST has now been operational. We've increased the number of galaxies that we've known at this time by a factor of 10 compared to the whole 20 years before the Hubble has been operating, which shows how great JWST is at finding these objects. And a lot of the work that our group in Manchester has done has been purely on the imaging side. We've not even looked at the spectroscopy side yet, where we can look at these galaxies in more detail. Yeah, I think I'll finish it up there. Okay, if anyone has any questions, feel free to shoot.
Actually, yeah, I should have one. You said so obviously at the start, the demand for the images that JWST we released was quite a competitive area. You're working on it right now, sort of like compared to the start. How competitive is the sort of field?
At this point, everyone's kind of the low-hanging fruit side of it has gone. So people are more doing their own thing and settling into larger scale projects.
Got it.
So it's not as bad as it used to be. There are still some data sets that as soon as they're released, people are jumping on. And it's not as bad as it was. Yeah, definitely when the first 3 months or so, it was a case where papers were being written and published in a week. Whether they were all good or not, I don't know. Whether they were all right or not, I don't know. But it's definitely calmed down. There's a lot less stressful than it was. But that said, the telescope is still very highly in demand, and it is the second most in-demand telescope that's currently out there. They do a proposal cycle that's yearly. So every October, people submit proposals, and then they get reviewed over the Christmas time, and then they choose which proposals they're going to do, like for the upcoming year. And every year, they accept around about 200 to 250 proposals, and this year, about 2,000 were submitted. So it's about 10 to 1 thereabouts, the number of proposals being submitted versus the number of proposals actually get done. There's only one telescope that's worse than that, which is Muse in Chile, which is about 16 to 1. Yeah, James Webb is up there with the most in demand still.
So you mentioned that there was that 20% error initially in the first few months. How was that actually discovered?
So it was the James Webb team at Baltimore. So Baltimore's where the Space Telescope Science Institute is, which is basically where the ground control is for Hubble and James Webb. So it's the actual engineers that work on the system day to day that kind of just published a message that was like, hey guys, we've got updates to calibration, so things changed by 20%. Some of the people that claimed early on that they were breaking the universe then had to very quickly retract those claims that they were breaking the universe. When I say breaking the universe, I mean like they're finding results that don't like comply with models of cosmology and things like that. It turns out that most of those things were because of the calibration errors. But yeah, after the first few months, we got it down from about 20% and then the Space Telescope said, we think we're good to 5% now, and that's good enough for most people's work. For people who work on transient astronomy, which is looking for things that change with time, like supernovae and things like that, 5% is not good enough, so I think that they were a little bit upset to start off with. But a year later, they think it's good to about 3% or lower now, which is more what they're happy with.
Right.
Thank you.
Okay, thank you everyone for coming. And obviously just a big thanks to Nathan for this amazing talk. Everyone wants to just give him just a second round of applause. But yeah, before everyone goes, Astrosoc tomorrow is doing their final weekly meetup of the year. We're going to have Christmas karaoke, hot chocolate, things like that. So everything's on our Instagram if you want to come. But yeah, I think that's everything. Have a good rest of your day, guys.
Thank you.